about, the title of the talk is Parallel I/O with HDF5, but I give everybody the benefit of the doubt that you may not have worked with HDF5, let alone parallel HDF5. So I will give you a quick introduction into HDF5 along the way, and I will make it easy for you. I'll just show you two movies. Of course, the reality is that if you are not familiar with HDF5, then picking up HDF5 and parallel HDF5 in one talk is a big ask. But yeah, we'll see. Okay, here's a bit of an outline. I would like to try to talk a little bit about the sort of problems and goals that we have. Talk a little bit about, as with everything else, if you want to improve the I/O performance or develop an I/O layer for your application, it's good to follow some strategies, some methodology, and I'll talk a little bit about that. Talk about the tools, starting with parallel HDF5, then you've heard about Darshan and things like that, so we'll talk about diagnostics and instrumentation. I'll give you two examples where people have successfully taken certain actions to improve their parallel I/O with HDF5, and then part of that will spill into the hands-on. We'll talk about sort of doing more with less, doing sort of achieving more with less writing code, and we'll talk a little bit about HDF and Python, just to get you started quickly in case you haven't really worked much with HDF5. There's no point in sort of writing a lot of C or Fortran code that you will ultimately throw away just to experiment a little bit with a few features. And Python, I think, is almost an ideal environment to sort of get started. Also, for the younger among you, these are book covers shown on this slide. These are resources that I have drawn on to put together this presentation that I highly recommend. On the upper right, this book on parallel I/O, there's more than just about, it talks a lot more about than just HDF5, and it talks about sort of the whole spectrum of activities in parallel I/O, from sort of benchmarking, performance analysis, high-level layers, and so forth. So I think this is a wonderful book, and I always, as far as parallel computing was concerned, my main concern was always I wouldn't spend any money on them because they're outdated so quickly. But I think this book is one of the few exceptions in that field. There's a lot in there, kind of, in my opinion, timeless material. So if you want to get up to speed on the breadth and depth of parallel I/O, I highly recommend you take a look at this book. And then for HDF and Python, there's Andrew Collette's Mr. HDF5's O'Reilly book. And then if you are interested more sort of in a more application-oriented view of sort of the Python ecosystem and I/O in particular, I can recommend this book by Anthony Skopatz, Effective Computation in Physics. Okay, let's talk a little bit about problems and goals. I'm sure, I haven't been here, but I'm sure you have seen that quotation several times already. There's a lot of truth to it, and you might be faced with problems like you're starting to write an I/O layer for your application, and right out of the gate, you realize that you're spending way too much time in I/O for reasons to be discovered. And if you then start scaling your application, you got all your science down, your verification, your validation is all great, and then you start scaling out your problems, you realize that this I/O bottleneck opens up right in front of you, and you have to figure out if and what you can do about it. Also, you talk to all the consultants and administrators, and they tell you you can get peak a terabyte per second throughput on that Lustre file system or something like that, and then you look at the actual performance that you get in your application, and you get less than 1%. You would be happy if you then got 1%, but you get a lot less, and then the question is, well, what can you do about that? There are a few common causes of I/O problems. The first would be that your I/O system is just undersized for the compute partition that will generate the data. that will either consume the data or consume the data, but also produce a lot of new data along the way. It could also be that system as a whole is just misconfigured for your particular application. Other users might be reporting great performance and they say, we can't understand why things don't work for you. But there might be something special about your application that makes it different, and the configuration may not be optimal. Then, of course, there is interference with other applications. I mean, all these big systems, everybody wants to get on them and get as many cycles and cores as they can get. And there is some interference sometimes because of different characteristics. And just the way your application reads and writes data leads to poor I/O performance is probably the strongest contender or the most likely scenario. And in truth, sometimes it's not necessarily your fault. Now, if you want to do something about it, again, you have to adopt some kind of methodology. Otherwise, it's just, you can win the lottery, yes, that happens every week, but it's important to be methodical about when you try to identify sort of the root causes and what kind of action you can take about the things that you identify as potential bottlenecks and so forth. Well, sort of on this list, 1 through 3 are kind of the easy ones because you can rule out or quantify them to some degree by running benchmarks, or then, for example, as far as interference with other application goes, by just doing repeated runs. It's very unlikely that the world is so perfectly synchronized that all these other guys that tend to interfere with you run during these repeated runs again and again simultaneously with your application. You certainly want to characterize your application through some kind of profiling tool, and as a result of all that, and knowing something about what your application actually does, you want to come up with some kind of performance improvement plan. And of course, a big concern here can be that there is sort of a whole lot of, or a spectrum, as I would say, of control that you can exercise over your application or the I/O layer. In the worst case, you are dealing with sort of something that is nowadays rather unlikely, but nevertheless possible, is you're dealing with something that's closed source, binary. You have absolutely no control over what's happening in that magic I/O layer. And in that case, unfortunately, there's not that much you can do. On the other hand, you or somebody you know has actually written that layer and is intimately familiar with it. You have the source code. You can just go in there, extract I/O kernels and things like that, annotate it, instrument it. And so there is a spectrum of control, and sort of going into such an improvement plan, you should be clear, or you should have some bearings as where in that spectrum you are. And then, of course, you have to know generally what your system's capabilities are. So, of course, if you work on these leadership class systems, well, they have that name for a reason, and typically you wouldn't expect that they are sort of undersized, underspecced, and whatnot. But nevertheless, talking to a consultant might help you to sort of set your expectations and sort of calibrate your goals. And of course, you have to be prepared to settle for a lot less, because even if you do all these other things right, there is still this something that's special about your application or this particular feature in the software or the hardware that you just can't overcome. But identifying it and coming up with rational explanations why this is to blame for not getting 100%, but 80% is still a good thing. Now, most of what I'm going to tell you next is common sense, but it deserves to be repeated, because I tell you all these things, but I can also tell you I've violated these rules many times myself. Of course, you want to prepare some kind of baseline, and there already you have to make a decision if you want to deal with a full-blown application. In some cases, you may not have a choice. You are dealing with a full-blown application, or if it's rather time-consuming. So, for example, there's a lot of computation involved, a lot of activity that has nothing to do with I/O. Well, it probably makes sense to try to isolate the I/O intensive part, and then sort of simulate the computation or just create some synthetic data to really study what's going on in terms of I/O. You want some kind of performance model, and that in the simplest case just means to do some back-of-the-envelope calculations. You know what you're reading, you know what you're writing typically, you have some general characteristics about the hardware that you are running on. So you can come up with some metrics and some expectations that help you to set some goals of what you would like to achieve. And then, of course, you want to do application runs with representative workloads. Of course, if the code is or the application is in very early stages of its development, you may not have yet representative workloads because they say, well, now we are doing toy problems, but next year we want to scale this out to the size where we can get some meaningful scientific information from this. Another part is in your sort of performance improvement effort is you want to define the search space. It's a little bit like when you're solving differential equations. Well, if you don't know the function space in which you are looking for a solution, you're really just shooting in the dark, more or less. And you want to define sort of what I would call loops of investigation, because typically you may not return repeatedly to the point of departure, but you will come to into the vicinity of that point of departure frequently. And as you sort of pursue these lines of investigations, you definitely want to keep track of sort of the setup and the results. And of course, you want to go for the low-hanging fruit first and keep the number of variables that you investigate small. And of course, never change more than one variable at the time. And of course, all this is ultimately constrained by the level of control and what your budget is. So if you have no budget or too small a budget, then that has to factor into all this activity or into sort of framing that activity. And then another one that's kind of interesting is you have to know when to stop. And that's sometimes difficult. You may have reached your goal. I would say in reality, that's unlikely most of the time. You have exhausted your budget. That happens quite often. You've gotten on a path of diminishing returns. That's very likely to happen. But realizing that you are on a path of diminishing returns, I think that's the crucial thing here. And then what you will find if you've been successful is that once you have been successful with sort of optimizing your I/O performance, improving your I/O layer, you will have a problem will pop up in a different part of the code. And then at some point that will return to you when it gets translated again into an I/O problem. Okay, let's talk about tools. Sort of what are the kinds of tools that we can bring to bear in such an activity. We'll talk about HDF5 in a moment as our main tool. We will need some kind of diagnostics and instrumentations, and today's systems are much better equipped in that department than they were 10, 20 years ago, for sure. And of course, some basic facts about your machine's I/O stack and capabilities. This talks about parallel HDF5, but I will actually start with a little bit of an intro into HDF5. And I call it HDF5 in 2 slides and 2 movies. First of all, a little bit about ourselves. We are the sort of developers, maintainers, owners of HDF5, the HDF group in Champaign, Illinois. Until 2006, we used to be part of the NCSA, the National Center for Supercomputing Applications, but then we spun off as a not-for-profit company because we realized that with the demands, with the sort of, as a business, you have to support customers and so forth. This is something that is very difficult to set up in a university environment where sort of the focus is on publications and so forth. And what is HDF5? I think the easiest way to think about HDF5 is a smart data container. It's just something that you can put data in a way that is very user-oriented and very portable, in the sense that you put certain abstractions into that container. And if you take it to a different platform, be it from one supercomputer to the next, or from a supercomputer to a scientist's desktop, or into a server, into the cloud, the abstractions and the metadata and all that travels with it. And it's portable. It doesn't matter if that was a power processor, or it will be an Intel processor, or there was GPFS here, and then all of a sudden there's a different file system over here. So a portable, a smart data container that gives you that portability for your data. Where is it being used? It is being used virtually everywhere in any realm of life, so to speak, in academia and enterprise, government, research, and so forth. We would like to believe that you should always use HDF5. The reality is, of course, not. When in doubt, talk to the experts, talk to us. There is the HDF forum. There are discussions on sort of software that supports HDF5, like MATLAB and Mathematica and so forth. In their forums, they have lots of information, lots of good information available. People make jokes about HDF5. We can talk about that tonight. And how can you get up to speed fast? Well, look at the books that I mentioned in the beginning. There's other great material out there. I'm trying to do a reasonable job in this presentation. Okay, let's start with the first movie. This is a movie that was produced for the HDF group by a company called Nthought. Nthought specializes in is one of the companies that specializes in creating training materials in the Python space for anything around Python, visualization, data analytics, and so forth. And they did this first video for us. This is an entire course, an entire curriculum on HDF5 and Python. And I'm going to show you two of the movies in the beginning, but it's a much longer course. But I think it gives you a great first introduction into HDF5, and it's, I think, just 7 minutes.
In this course, we explore a technology called HDF5 and see how to use it within Python. HDF5 lets you organize, access, and share
large amounts of information, along with the context that makes it useful. Although HDF stands for hierarchical data format, as you'll see, HDF5 is much more than a simple file format. It's a powerful way of organizing information, an extensive but easy to use programming API, and a rock-solid, high-performance software library maintained by a dedicated nonprofit organization. Over the past several years, HDF5 has become a commonly used technology in the Python and NumPy communities for handling large numerical data sets in an organized way. To get started, let's discuss the kind of problems that HDF5 is designed to solve. Real-world problems come in lots of different shapes and sizes, but many share one common theme: the need to manage a diverse collection of data objects. Not only can a scientist or developer become overwhelmed by the sheer quantity of information, but it can be hard to figure out how to organize that information in a way that can be easily understood, maintained, and shared. Other common themes apply to any technology used for managing data. For example, it's highly desirable that a solution be high performance. In other words, that it support reading and writing data quickly. Another is the ability to scale to large data sizes, much larger than will fit in memory, and sometimes larger than will fit on a single computer. Likewise, any solution should be flexible enough to handle many different kinds of information and relationships between data elements. In other words, it should support heterogeneous data and diverse organizational structures. HDF5 addresses these areas in different ways. To get started, let's talk about one of the most common challenges in data management: handling many pieces of information of different types. Let's suppose we wanted to record the results of an experiment. In this example, we're developing a new kind of machine, performing field tests for a new kind of aircraft engine. The results of a test don't arrive together in a neat bundle. Instead, we have a set of data from the engine and aircraft electronics, another containing sound and voice communication over the radio, another with GPS information as a function of time, yet another with video and image information from the ground, along with weather records, radar data, and so on. how should this information be represented? And more importantly, how can we organize it in a way that lets us draw conclusions about the test? Let's see what happens when we try to record this information using common methods based on a file system. First, we'll have a written log, maybe a text file, containing notes about the test. Then, we'll have an image series, which tracks the aircraft as it goes through the trials. We'll also have sound and voice recordings, then raw data on aircraft performance, some additional sensor readings from various equipment on board. We also have a video series recorded by an onboard camera. In later tests, more camera angles, and more, and more. And finally, we have the results of our test as a big pile of disconnected pieces of data, all stored separately in their own formats and with their own metadata. This is how it might look on the computer. The data consists of a number of files. How do we keep these files organized? You might notice one common approach, seen here. We put the information in the file name. That's because, apart from format-specific information, like image size and color depth, the only place we can add context information is by editing the file names. We might introduce a naming convention, reserving sections of the file name for things like the date, the trial number, or an image count, for example, 001, 002, and so on. Or we might decide to create a directory structure that captures some of this information. But that creates another problem. Since each file can only go in one folder, we have to decide ahead of time how to organize the data. So, for example, we might have a folder containing all the data records for a particular flight. This works well if we want to retrieve all data on a per-flight basis. But what happens if we want to read just one piece of data, for example, engine performance, across all flights? Or if we're testing more than one prototype? With this kind of system, just figuring out how to extract the data we want can become a time-consuming and error-prone step in the analysis workflow. It's also fragile and inflexible. It becomes tricky to move things around, for example, once you start writing scripts that assume particular files are in particular locations. These problems can certainly be solved, but it's a lot of work. And of course, we have to manually synchronize all this information with the notes in the experiment log. The image files, for example, only carry information about their shape and color space, when it would be useful to also know what part of the aircraft they track. HDF5 is designed to address these issues. As we'll see in later lectures, HDF5 provides the means to not only store this information efficiently, but also to keep track of context information, or metadata, required to make sense of it. HDF5's metadata system allows you to store information right next to the data it describes. So there's no extra step required to give your data context. All the information is in one place. HDF5's grouping mechanism is much more expressive than folders and file names, and doesn't restrict you to an inflexible, one-size-fits-all tree of folders. Objects can be found in more than one group, which allows you to create multiple views on the same data and access it in multiple ways, whichever is best for your application. And you can also create new views on your data long after data has been collected, without interfering with the structures already in place. Using HDF5, all this information can be stored, organized, retrieved, and later updated, all in a single bundle. Here, the HDF5 file contains a complete representation of the experiment. This experiment can be analyzed, shared, or archived, all in one comprehensive and self-contained piece. Let's talk about another important area that HDF5 addresses, the need to handle larger data sets with good performance. For small problems, people often start off using text formats like CSV. They work quite well when data is on the order of kilobytes or megabytes. But at a certain point, the demands on disk space and memory become so large that the analysis process slows down. We find ourselves waiting longer and longer for what should be simple operations to complete. For example, just opening a data file. From the perspective of a user or developer, this is frustrating because many tasks deal only with a fraction of the data. For example, we might want to analyze only a few rows from a spreadsheet. We have a large file on disk and a smaller amount of computer memory available for analysis. This would be great if there was some way to read just the rows we want. They might fit into memory, and we could proceed. But more typically, workflows are designed around the assumption that we can safely load all data into memory at once, and at a certain point, this stops working. HDF5 addresses this problem by supporting partial I/O. In other words, the ability to specify just a portion of the data to read or write between disk and memory. From a Python developer's perspective, this means you can entirely skip the process of writing a data importer. As we'll see later, HDF5 datasets can be treated much like ordinary NumPy arrays that happen to be stored on disk. That means no writing parsing or reading code. Just open the file and retrieve the parts that you want. HDF5 is an excellent platform for sharing data. It's implemented by a high-performance, widely used open-source library. That means that your HDF5 files will work in Python, MATLAB, IDL, or any other platform that uses this library. It's very common in the scientific and engineering communities to use HDF5 for data interchange and also for archival use. Finally, it's important to note that HDF5 is supported by an independent, nonprofit organization called the HDF Group. The HDF Group not only maintains and improves the library, but provides many useful tools and serves as a hub of the HDF community. As you consider if HDF5 is right for you, keep in mind this data management landscape and where HDF5 excels. In this course, you learn how to use the tools that HDF5 provides within Python to develop solutions to a variety of common data management problems. We begin with an introduction to HDF5's extremely simple, yet powerful and flexible data model, organized around three basic building blocks: datasets, attributes, and groups. Next, you'll learn about some of HDF5's most powerful features, including partial I/O for fast data access, the self-documenting features of HDF5 files that help with maintenance and sharing, and compound data types that provide great flexibility and ways to store your data. Finally, we'll dive into some of the more advanced aspects of HDF5 that support efficient and scalable computing, including storage layouts and compression. And we finished with an overview of some handy command line tools that make working with HDF5 files even easier. Along with the video lectures, be sure to take time to complete the exercises. After all, the best way to learn programming concepts is by sitting down and actually doing some programming.
Okay, maybe it's the right time for a quick recap. It was mentioned in the video already. The HDF data model is actually very simple, and I think the simplicity is part of why it's successful. I mean, it doesn't mean that complex things can't be successful, but there's a better chance, I think, that simple things will be successful. So in this data container, an HDF5 file, although it doesn't have to be necessarily a file, as we will see later, but it's probably the most common way that this container is represented, you can define certain arrangements, you can group things, you can associate them in something that there's no harm in thinking about as you would arrange files or other objects, images, videos, for example, in the folders of a file system structure. And what we call sort of the heavyweight data, or sort of the variables that your simulation produces, typically some form of multidimensional arrays that are logically dense, but they could also be sparse. We call them data sets in HDF5, but you can also call them variables. It's really more a matter of choice of name. And HDF has a very rich system of types built into the library, into the data model, but then there are also facilities that allow you to create your own types, and that is true for what we would call atomic types like floats and integers and so forth. So you can define your own floating point numbers if the just standard IEEE floating point numbers don't do it for you, or you have a good reason based on the structure of the mantissa or exponent, the range, you might have knowledge that you might use to drastically compress and condense the data, and that might be a reason to define your own floating point data type. And HDF has facilities for that. And then you have a lot of control over the storage layout of these data sets, of these variables in the file. They can be stored, as we will see in a moment, as large contiguous blobs of bytes, but you can also tile them, you can apply compression, encryption, things like that to these tiles or to these chunks, as we call them. And then finally, one of the important things that the movie also pointed out was that there is a portable metadata layer built into HDF5. This is where sort of a traditional file system falls down. Yes, file systems may have their file system specific capabilities to express things like timestamps and access attributes and things like that, but those are not portable. The moment you move things into a different file system with different capabilities, that type of metadata goes away, and the capabilities vary largely. With HDF5, with so-called HDF attributes, you have a portable metadata layer that travels with the container, and everybody who opens the container will discover these attributes, that type of metadata that you use to represent things like in experiments, sampling rates, calibration factors, resolutions, and things like that, units. And everything else in HDF5 from a user perspective is pretty much built from these. It's generic, it's simple. We would be foolish to claim that this is the fastest, the best that you can do in any specific context. Of course, if you have a specific application, a very limited circle of users, ways to access it, a limited lifetime, you can always design something that's better because purpose designed for your specific application. You can do better than HDF5. But if you take into consideration, and that was sort of symbolized in that wheel, that what we refer to as the data life cycle, if you want something that sort of accompanies you throughout the data life cycle from sort of data generation or acquisition to the point of archival and retirement, you need something that is very portable, that is very durable, and we believe that HDF5 is an excellent solution there. I would like to show you a second movie that sort of talks a little bit more in depth about the data model and the options, and that's going to be the last movie. And then we'll talk about parallel HDF5.
In this lecture, we introduce the basic pieces of HDF5 and describe how they can be used to solve data management problems. In the modern world, analysis problems can be very complicated, with lots of pieces that interact. The result is large quantities of data that piles up in different formats and in different locations. Dealing with this large variety of file formats and locations takes up valuable time. For example, the need to write parsers or scripts that read information from different file formats is time not spent on analysis. Also, it's very easy to separate the data from the context information or metadata that's required to provide a consistent picture. Importantly, this is not only a problem with the sheer quantity of data involved, it's also a problem for sharing data. So what we need is a technology that can cope with large amounts of data of different kinds, while still providing fast, efficient access to that data, bundling metadata or context information that makes the data useful, and also allows us to easily share all of this information both across people and across platforms. HDF5 helps you solve this problem. HDF5 files provide data objects that can store numerical data, a way for handling metadata, which means you can provide context information, and also a mechanism to provide structure to indicate that different pieces of data have some relationship. In the HDF5 universe, this problem is addressed in an extraordinarily simple way. HDF5 provides only 3 data structures, which are enough to solve this entire problem. The first, data sets, are the equivalent of NumPy-style ND arrays that can be stored on disk. The next, attributes, are a mechanism for storing metadata in key-value form directly attached to the objects it describe. And finally, in a way similar to folders in a file system, groups allow you to bundle objects together and indicate that they're logically related. These 3 basic building blocks allow you to construct solutions to complicated domain-specific problems. To start with, Datasets are the mechanism in HDF5 for storing large quantities of numerical data. You can think of them as NumPy arrays that live on disk. Just like NumPy arrays, datasets have a well-defined shape and type, and they can be sliced. In other words, they support partial access, and you can read only the portion of that data that you want. This is very important because in HDF5, there's no practical limit on how large a dataset can be. It's very easy to create and manage multi-terabyte datasets in HDF5. And because HDF5 is platform independent, the files that you create can easily be shared not only between computers, but also between environments. The next piece of HDF5 is attributes. Attributes allow you to attach key value metadata to any object in the file. Importantly, this means that metadata, or context information, is always located right next to the data it describes. So, when you share your information with other people, they can very easily understand what it means. All the information required to make sense of your data is stored right there in the file. This is a big part of what makes the HDF5 a so-called self-describing format. In other words, you can interpret the meaning of the data without having to reference other documents. For example, you might have an array or a dataset in HDF5 that contains image information. This would be communicated by a series of attributes that describe properties of the image. The final HDF5 building block is groups. Groups are an extremely powerful way to organize objects in your file and provide structure. Much like folders in your file system, HDF5 groups are used to represent logical relationships between objects that have different shapes or types. And because groups can be discovered and browsed, much like folders, they're a big piece of making your HDF5 data self-describing. What does it mean to be self-describing? In the HDF5 world, it means that you can skip the step where you write a long parsing script to pull data out of a file. In Python, this means you can interact with groups, attributes, and datasets in a very Pythonic way. In other words, groups and attributes use the dictionary metaphor that can be iterated over. They have keys and values. And datasets behave like NumPy arrays. You can slice them, and you can examine attributes like shape and dtype. It also means that files you write from Python can also be explored in other environments that support HDF5, like MATLAB. And this extends to any HDF5-aware tool. For example, the graphical viewer program HDFview can understand any file that you write, because both of them use HDF5. HDF5 comes with many other features that can help to solve problems. For example, much like the NumPy structured array, you can define compound types in HDF5 that represent table-oriented problems. HDF5 datasets, created with the right options, can also become dynamically resizable. So, for certain problems, where you may not know ahead of time what shape you want, HDF5 can adapt. HDF5 datasets can also provide transparent compression, which means that you can read and write data as normal, but HDF5 will compress that data when stored to disk. And HDF5 comes with a variety of different storage methods that allow you to optimize access for different use cases. Let's talk about how people use these HDF5 building blocks to solve problems in the real world. In the HDF5 world, conventions are a standardized arrangement of groups, datasets, and attributes that are used to solve a domain-specific problem. Here's an example. BAG is used by the ocean science and navigation communities to describe ocean water depths. So, a BAG file holds 2D datasets that represent the depth and uncertainty of the depth over a particular area of the sea. In addition to that data, attributes are used to hold information summarizing the full range of values. And other datasets in the file hold information about who created the file and how it can be used. Another example is the MINC format. Like BAG, the MINC format is a series of conventions on top of HDF5. It's used to represent medical imaging data. In MINC, groups are used extensively to bundle datasets that represent an image. Likewise, information on location required to make sense of the image is stored as a series of datasets under a dimensions group. And attributes attached to both the groups and the datasets provide essential information on the orientation of the image, how it was acquired, and other details. So, to summarize, HDF5 is based on just 3 simple elements: datasets that store numerical data, groups that provide organization and structure for that data, and attributes that provide the context information required to make sense of it. Datasets can handle very large amounts of data and can be of many different types. HDF5 provides fast, effective partial I/O that allows us to read and write only portions of the data that we care about. Attributes allow you to store context information or metadata in the file right next to the data that it describes. Groups provide the organizational glue that holds it together. Together with attributes, good use of groups make your HDF5 data shareable, discoverable, and self-describing. And finally, communities, which can range from a small lab to a large standards organization, can agree on conventions on how to use groups, datasets, and attributes to represent a problem.
Okay, maybe before we switch, just to round this off, HDF is a technology, is a piece of technology, but it is what it is only because there is sort of a whole ecosystem around it. And by ecosystem, you can view that as all the software that's written to produce HDF5 that consumes HDF5, but it's also, as the standards discussions, for example, illustrates, it's about standards bodies adopting HDF5 or another file format to serve their community as a way to communicate their results, to communicate their research. And there are a lot of supporters out there that actively support us by reporting bugs to begin with, but also fund the introduction of new features into HDF5, and that really keep pushing us to make HDF5 more robust, better, faster, and bring it into hardware environments that it hasn't been used traditionally. And I mean, everywhere in sort of computing, be it storage, be it networking, there's something new every other week, and as much as we can, we'll try to follow that. Now, you've probably heard terms like data and metadata a lot over the past few days, and here's just a little bit of a clarification. This is the way I will use these terms. When I talk about data, I refer to what one would call sort of your problem-size data, which is you do a finite element simulation, for example, the number of degrees of freedom would be that problem size. And anything like a stress field or velocity field or something, that's problem-size data. And they would be represented, for example, in large, dense arrays, for example, in an HDF data set or in a netCDF variable. Metadata is an overloaded term. I will use it kind of in two ways. One way is sort of, as we saw in the video, this sort of what one might call descriptive metadata or application-oriented metadata, which is keep track of calibration parameters of your instruments, timestamps, and things like that that mean something to the user and that the user needs to interpret the data. But in this presentation, as we talk about parallel HDF5, there is a lot going on under the covers, and I refer to that data as HDF metadata, things that have to do with file internal structures, auxiliary structures like heaps and B trees and things like that. So there's a lot of metadata in the sense of HDF metadata that is also there and has a great influence on performance. And typically, as you can say, for each piece of application metadata, there's at least one, but typically there are multiple pieces of HDF metadata, and that's what also causes some of the performance problems, as we will see in a moment. Why parallel HDF5? Well, obviously, if you like something in the non-parallel world, you would like to maybe bring that over into a parallel environment. But as you've learned over the past few days, is that doing I/O and sort of working with all the great tools and getting the stuff done that you would like to get done gets pretty complex pretty quickly, and getting good performance is even harder. So we see parallel HDF5 as an attempt to add a well-defined thing in the sequential or serial space to the parallel stack, to the parallel I/O stack at a certain position, not at the lowest level. We are sort of based on MPI-IO, for example, in the picture of layers. And another thing that users find very convenient is, of course, you want to keep that dream of the single container, of that single file alive, because it's just easier and might be something worthwhile to have. And then, of course, this is more sort of more funny or not so funny, is you can do, and you can get great results sometimes, and sometimes it's the only way to get good performance is to use one file per process, but if we can avoid it, then I think most would agree that that's something you want to avoid. And sort of in that portability theme where we think of HDF as this portable smart data container, of course, ideally you also want to port performance, because every 3 years, every 5 years there is a new system, and wouldn't it be great if you could, in relative terms, sort of take the performance from one system to the next, and the next system might have faster I/O subsystem, faster CPUs, and so forth. But you, in relative terms, you don't want to lose performance on that new system. So wouldn't it be great if you could, with the data, take also the performance of the application with you to the next platform? What we will cover here is, and that's sort of a way to define parallel HDF5 by contrasting or comparing it with how you would use it sequentially. We'll talk a little bit about the implementation layers, what happens to how an HDF5 file actually appears to a parallel file system like Lustre or GPFS. And then we'll talk, you've heard a lot about collective and independent I/O already, so we'll cover that from the HDF perspective. And then talk about some of the challenges and heuristics that you can apply when you do data and metadata I/O with HDF5. And again, data and metadata in the sense that I defined earlier. Data is sort of the problem size stuff. Metadata is sort of the annotational stuff in the application sense, but then also a lot of the things that make HDF work under the covers. There's a lot more to HDF5. So I just give you, and this is something we can talk over dinner or later today. We won't cover here questions like consistency semantics, metadata servers. There's a thing called the virtual object layer in HDF5, automatic tuning. We just released HDF version 1.10, which is the next major release, where we introduced features like swimmer or single writer, multiple reader, so-called virtual data sets, big I/O, and the list goes on. See me after the break, or we can, if you have interest in one of those topics specifically, we can cover them tonight. Now let's compare parallel and serial HDF5. At sort of the most basic level of understanding, it allows multiple MPI processes to perform I/O against a single HDF5 file or against a single file. It uses, as that definition implies, it uses MPI I/O as its layer, so we don't reinvent parallel I/O in any shape or form, and that's one element of the portability story. Any system, well, to port HDF5, the HDF library, you just need a C compiler, and that's an advantage if you want to port HDF to an embedded system or anything where you have a C compiler. You can compile the HDF library and create HDF5 files or read HDF5 files. For parallel system, if you have MPI I/O, you are capable of using parallel HDF5 on that platform. In terms of the file format, and this is where people sometimes get confused, there's only one HDF5 file specification. If you go to our website, hdfgroup.org, in the docs section, there is the file format specification, or there are different versions, because now we are on version 4 of the HDF5 file format specification. That specifies sort of the byte level layout of HDF constructs in HDF5 files. There's only one such specification. There's not a separate specification for parallel HDF5. A parallel HDF5 file is sort of a misnomer in the sense that it's an HDF5 file. Parallel speaks to how that file maybe was generated. It talks about the process of that generation, but from a file that was generated as a result of parallel HDF5. It's indistinguishable from a file that was created otherwise. And so in a way, if you want to look at it a little more in technical terms, the parallel HDF5 file, the parallel HDF API is really the standard HDF API that's available to you. But in addition, you get some additional sort of knobs and calls and some guidelines of how you have to use some of these additional capabilities. So as a bottom line, we really try to make parallel HDF5 as user-friendly as the non-parallel HDF5. And of course, when I say parallel here, and that's sort of indicated in the title by these parentheses, I'm talking about MPI parallel. In the hands-on, or we later talk a little bit about other forms of parallelism like multiprocessing or multi-threading. Here, when I say parallel, we strictly speak about MPI-IO parallelism. Now, this is sort of the standard skeleton of an HDF5 program in a language. I mean, it looks a lot like C, but a Fortran program or even a Python program would have a very similar structure. The only difference in Python or sort of some of the other scripting languages would be that they do garbage collection and sort of they close handles automatically for you. So some of the close calls are not necessarily visible to you in the source code of a program. But this is sort of the standard skeleton of an HDF5 program where you create a new HDF5 file or you open an existing file, and then you would sort of, if you want to create a new variable in netcdf speak or a data set in HDF5 speak, you want to first describe things like what's the shape of this new variable that I want to create, what is the type of the elements that I will be storing in that data set, and of course, as we see here already, each of these create or open calls is matched by a close call. This is just for housekeeping, that there are certain handles associated with every new object that you create in HDF5 in memory or on disk, and you have to free those handles. And again, in some environments, that's done automatically for you, but in C or in Fortran, you have to do that yourself. And then, so once you've created your variable or your data set, you can read it from disk into memory, or you can write it from memory into a file system and so forth. And this standard skeleton actually does not change in a parallel context. Now, what changes in a parallel context is you are confronted, at least physically, with this sort of layer, with this stack of layers, and you have to keep that in mind. Once you want to improve performance, there are sort of knobs and activities that live in different layers, and not all of them are just HDF5. Some of them are related to the MPI-IO library, some of them are related to the Lustre file system and whatnot. So on top of that, you have your application, so to speak, then the compute nodes, those are sort of the engines that are actually executing your simulation, running your code, and they make calls into the HDF5 library, which in turn calls the MPI library. Of course, using the HDF5 library does not prevent you from using other capabilities in the MPI library in addition to HDF calls, but we try to make this as convenient for you as possible. But you still have the ability to do sort of to bypass this layered picture to some degree. And then, of course, the MPI library in turn interacts with Lustre GPFS, and then at the hardware level, you have sort of a highly scalable network and I/O servers and so forth. Here is sort of a snippet of a parallel HDF5C program, and I tried to highlight in red here the things that are new compared to what one would call a sequential HDF5 program. Of course, you have to initialize MPI, that's a given. And then the way to tell the HDF5 library that we are doing sort of a non-standard thing, a non-standard meaning sort of traditional POSIX sequential I/O, is in HDF5 we use these so-called property lists. DCPL, and there is sort of a naming convention to some degree in HDF5. So a FAPL, for example, is a file access property list. A DAPL would be a data set access property list. There are also creation property lists. So a DCPL would be a data set creation property list where you would specify, for example, things like if you want to use compression for the data set elements, or if you want a particular storage layout, you would create a so-called data set creation property list, and then pass that property list to the H5D create, which would be the call to create an HDF5 data set. But in this case, we announce our desire to the runtime to use the MPI-IO layer by creating this file access property list, where we basically pass an MPI communicator. So it doesn't have to be necessarily MPI convert, it can be any MPI communicator. And then we use MPI info objects to sometimes pass heuristics to the system, like collective buffer size or other. I mean, there might be there are different optimizations, for example, for GPFS and for Luster, and some of them you can sort of conveniently encapsulate in MPI info objects. And then, as far as we heard a lot about collective I/O and so forth, so in HDF5, the way we do this here, we have this H5D write call where we actually write an array of some type, and we tell the library that we would like this call at the underlying MPI level to be handled as MPI-IO collective. We do this through a so-called data transfer, DX stands for transfer property list. So we would create such a property list with the property H5FD MPI-IO collective, and then pass this data transfer property list as an argument to this H5D write call, and that's it. And then of course we call MPI finalize at some point. But it's really it looks like a standard HDF5 program, if you wish, with a few bits and pieces sprinkled in to sort of target or address some of the parallel issues or optimizations related to parallel I/O. And so, for example, for these property lists, there's always, in a way, if you ask, well, what's the deeper purpose of these property lists? The deeper purpose of these property lists is, as Rob mentioned already, the HDF5 API is huge. There are hundreds of calls in sort of grouped in different. Well, there aren't any namespaces in C, but they are sort of grouped by API. Things that are dealing with data type management, for example, there is an H5T something. So if a function, for example here, H5D, right, anything that starts with H5D has to do with data sets in HDF5. H5T has to do with data types. H5A has to do with attributes and so forth. So the API being huge already, of course, we try to do everything to not grow them intentionally, to not continue to grow them intentionally to sort of an unbearable size. And again, this is C that we are talking here, and the HDF5 library is written in C for portability and other reasons. In a way, to stave this urge to introduce ever new API calls is to basically have these things that we call property lists. And then basically, instead of defining a new API, you just define a new property. So that way, you can convey to this rather generic H5D write call, by the way, use collective for this, or tell it something else. Do a transformation. As you write these data, rescale the data, or do something to the data. But you encode that all in this property list, rather than defining two more H5D write variants. And so that's sort of the flavor of a parallel HDF5C program. Now, earlier I mentioned there are sort of the additional knobs and APIs, but then there is also an etiquette that sort of rules of behavior or how you should apply these. So parallel HDF5, as we just saw, opens a shared file with an MPI communicator. It can be MPI conworld, but you will typically have sort of subsets of processes that will deal with I/O, and they are together in their own communicator. So you will use that communicator, and that returns one of these file handlers. And all future accesses to this file will happen through this file handle. And for collective calls, and we'll talk about collective calls in a moment, all processes in that communicator must participate, must invoke these collective calls. And of course, you can open different files through different communicators and so forth, or multiple files on the same communicator. That's up to you. But as far as sharing files goes, that has to happen on one communicator to the processes that intend to read to or read from or write to that file. And in particular, if you ask, well, what sort of a rule of thumb for which of these calls are collective and which aren't? Well, one of the main reasons, not the only, but one of the main reasons that we require certain calls to be collective, they have to do with sort of the coherence with the integrity of the HDF5 file, in the sense that you don't want a situation where one MPI process creates an attribute and then another process tries to create the same attribute a little later. So you really want a coherent state that, so when an attribute is being created, it is visible to all the other processes, and everybody has sort of, at least logically, the same view of what's in the file and what isn't. And so any structural changes that you make, create new objects, decorate an object with an attribute and so forth, they tend to be in this list. If you go to that URL, it sort of tells you for every HDF5 call if it's collective or if it's required to be collective or if not. And as we saw, some calls like writes or reads sometimes, they can be either way. They can be collective or not collective, or independent, as we would say. What happens to an HDF5 file in a parallel file system? Well, it's not looking good. Because what happens, okay, we have this great definition of the sort of the byte level layout of an HDF5 file, and now you take that byte stream, and that byte stream is composed of sort of metadata and data, and they can be arbitrarily interspersed, because as the user sort of writes data to a file, as we saw in the presentation earlier, there might be video mixed in with other things. And then if you think about situations where you record a time series, for example, or you have a simulation that's time dependent, you keep appending data to that, and in between sort of writing checkpoints or writing data, you create new attributes and so forth. So in terms of the file, it's a total mess. Stuff is just all over the place and interleaved. And yes, there is, at the HDF5 file level, things are interlinked and so forth. But what happens if you take that big byte stream and put it, for example, into a Lustre file system, but GPF is the same story. It's like taking scissors and cutting it up into pieces that are convenient to that storage layer, and so well, then you can ask yourself, well, what am I going to do with that? Well, the HDF5 library tries to sort of hide that from you as much as possible, but sometimes you just see side effects when this goes wrong. So we talked a little bit about, so drilling a little deeper into this, we talked already about when you store problem-sized data, these variables or data sets, as we call them in HDF5. One way, the most straightforward, and in fact the default way, is to store them, if they are fixed size, as one contiguous big C row order, row major array on disk. And then the metadata that might be associated with that, so let's say you want to store a temperature field or a velocity field, and then you have some attributes associated with that about the units of that or the identity of the weather station, for example. You will have some metadata with that, and that's sort of the default layout. And in some cases you might think, well, if I keep track of the addresses and so forth, I can always sort of find that and then maybe do some things with MPI-IO. So that's not that bad, but it gets worse. So again, for some of the flexibility that you have in HDF5, for example, when you apply compression or you want to create variables or data sets of a variable or infinite for all practical purposes in an extent, you can't store that contiguously because you don't know at runtime, well, how much space should I reserve for that thing? And the user might always the application might always come back and say, oh, by the way, I would also like to write that, and then you're not going to do a big realloc or something like that. So the way HDF deals with that is really you take that logical data set and you break it up into tiles or chunks, as we call them. And that works for anywhere between 1 and 32 dimensions in HDF5. We don't have many users that use 32-dimensional data, and there's no logical reason why 32 should be an upper limit. It's just the air gets pretty thin pretty quickly, and people probably don't use more than 6 or 7. I have never seen anything greater than 7. Now, well, with that, it sort of, and if you think about that picture with the OSTs, with the Lustre OSTs, for example, or the GPFS servers, then it gets messier and messier because at the HDF5 level, we now have to keep track of where these tiles or chunks are located in the file, and there are different structures how you can index that. And in HDF5, we support different ways to do that. The most traditional way that's sort of tried and true would be something like a B tree, but you can also use just arrays or hash tables, and depending on the nature of the data and the dynamics, you will use sort of different strategies of sort of keeping track of the location of your data in the file. Now, again, looking back at this picture, now we are cutting up something that is fragmented already. We don't have these nice big contiguous chunks anymore. And again, from a performance perspective, what you've heard over the previous days, well, if people find I/O challenging with MPI-IO, it's certainly low level and so forth, but it gives you a great level of control over where your bytes are placed and so forth. Now you are 2 layers almost removed from that. Well, it takes a leap of faith to some degree to convince yourself that, yeah, maybe HDF can handle these things for me reasonably, or, well, what can I do? What kind of information can I give HDF5 so that hopefully the right things will happen for me under the covers? Let's talk a little bit about collective versus independent. The MPI definition of collective calls says pretty much, well, everybody in the communicator must participate, but also that participation has to occur in the right order. So for example, if you have 2 MPI processes and the first one calls API A, and the second process also calls API A, and then they both call B, that's right, that would qualify as collective calls. However, if the second process for some reason or control flow decides to do these the other way around, that wouldn't count as collective. And then, of course, the opposite, or not exactly the opposite, but the contrast of that would be independent, but there isn't really a good definition of independent. It just means it's not collective, at least in HDF5. And also, collective, that's important to remember, collective does not mean that it's necessarily synchronous, nor does it mean that there has to be some kind of communication. So only because we decided to do things collectively, now there is necessarily this overhead because now we have to all orchestrate our interaction, our joint action. That's not true. Collective does not mean it's synchronous. It does not necessarily mean that it requires any kind of communication. It does so oftentimes, but not a priori. Collective I/O, and I think for as far as HDF5 is concerned, a convenient way to think about collective I/O, and then also think about when you try to determine, well, could collective versus non-collective or independent be the source of my problem here? A convenient way to think about it is, think of collective I/O as an attempt to combine multiple sort of smaller independent I/O operations into fewer larger operations. This is something that Lustre and GPFS and these parallel file systems appreciate. And so, for example, we talked about metadata and data earlier. In a data where we are talking about problem-sized large data sets and so forth, heuristically you can expect that the difference, unless your collective buffer sizes and your collective buffer counts are completely off, you wouldn't expect a drastic performance difference between collective data I/O and independent data I/O under those circumstances. Data in the definition I provided earlier, in the sense of the definition I just provided, and then, yeah, let's assume your buffer sizes and so forth are not way off the mark. With metadata, that picture changes. With metadata, we talked about, well, it can be just these little things, these key value pairs, and then HDF metadata that have to do with keeping track of the chunks and so forth, and then header messages and whatnot. The picture changes there. These are multiple, smaller, potentially independent I/Os, and file systems don't like them. And both directions, reading or writing, I think we heard an example earlier, what we call, and we'll come back to that in a moment, we call this the read storm, for example. If you take some of these community standards where people have come together and agreed and say, we are going to store our computational fluid dynamic simulations in the following way, and this is how we keep track of the pressure and the sort of calibration constants and whatnot, and then you have a parallel job where all of a sudden tens of thousands of MPI processes will open this file and all try to read the same piece of data. It's by default in HDF5 it would be an independent I/O operation, so you have this read storm where tens of thousands of MPI rings are just hammering on Lustre, begging for the same little piece of data. So in those situations, you can assume, or it's a good assumption, to say, hey, if I can do this collectively, the system will respond much better to that. And yeah, that's sort of a slight generalization of what I just said. If you are asking, well, what are sort of rules of thumb I can provide, or we provide for HDF5, for parallel HDF5, for data which are problem-sized, I/O can be independent or collective. Independence typically fine, so is collective, again, with the caveat that make sure that these buffer sizes are not completely too small. That's typically the problem. They are too small or they are too few. Typical improvement targets when you want to optimize your data I/O is, well, first and foremost, avoid unnecessary I/O. We are talking about problem-sized big pieces here. Frequency of I/O could be too high and unnecessary I/O in that sense. The layout on disk is going to be very important, and if there are any patterns, if they are irregular, of course, you would expect the performance not to be that great potentially. And load imbalances, things like that, alignments that you have control over, so a misalignment with where things get placed in the HDF5 file versus Lustre stripe boundaries and things like that. For metadata, again, they tend to be small if you think about their size. In HDF5, the reads can be independent or collective, and again, to deal with things like the read storm and so forth, you should strongly consider using collective I/O for that. All modifying I/O, the creation of attributes, the creation of new groups and things like that, must be collective. You have no choice there, and I think for your own good. And improvement targets, definitely the metadata design. So as you design the metadata, let's say you are part of a group of people who wants to standardize the way your community stores data in the file, keep that in mind. And it's also important, this is an area where we make a lot of improvements, and there were a lot of improvements. We talk about that in a moment with the latest release. If possible, use the latest library. I mean, HDF is open source and freely available, so in the worst case, you can get the source code and compile it yourself, but depending on which system you are working on, you may or may not have the freedom to sort of deploy your own version of HDF5. And then, of course, with these metadata, there are additional things. To give you better performance, the HDF5 library does a lot of caching. And in some cases, of course, you have to run some diagnostics and so forth and know something about your application. If you suspect that the metadata cache, the behavior, the default behavior of the metadata cache works against you, there are ways in the HDF5 library to take control of eviction policy or disable it altogether. Just as a reminder, don't forget that this is a multi-layer problem. It's not all HDF, it's not all application, it's not all MPI-IO. There are several layers, and sort of just spending your efforts and sort of your investigative energy wisely in these different layers can be a challenge, but it's always important to bear this in mind. There are things that you can try to address at the file system size with things like stripe factors and stripe sizes, at the MPI level with number of collective buffer nodes and the sizes and so forth. And then last but not least, at the HDF level with avoiding things like truncation. We come back to that in a moment. Dealing with alignment, sort of experimenting with collective versus independent and so forth. Of course, all this would be terrible if we didn't have, or pretty futile, if we didn't have some diagnostic capabilities that would help us sort of move in the right direction, or at least try to understand what is the root cause of the problem that I'm seeing. And I have a textbook example here that I'm not going to talk much about because it's really just a textbook example and typically doesn't happen in reality like that. It would be too easy if it were just like that, so I'm going to go quickly over this. Let's say somebody wants to write sort of columnar data, so each process owns sort of a chunk of rows, but they want to write data in a very columnar fashion. What you will see is that you get pretty poor performance, and to understand what happens is, again, this is not realistic because if you run this on large numbers of nodes, and the overhead is going to be terrible, misleading. The data that's being printed is just going to be garbled and everything, but okay, bear with me. With HDF, you can compile, when you compile the library for parallel, with parallel extension -- enable parallel, you can provide a flag called enable debug, which will give you very verbose information about MPI-IO calls that are being issued. And if you do that, you will get information about where it writes, how big of a piece of data it writes, and so forth. And that then will tell you that you are terrible, you are doing a lot of seeks, a lot of small writes, and so forth, and that's what gives you poor performance. And so when you change that, you define chunks that are, for example, columnar, or you use collective I/O, you will get better performance. But again, this is a very idealized application, and yes, you can pat yourself on the back if you sort of gone through this exercise, and you will see with collective writes the world is. But again, it's very synthetic and just for textbook. Back to the real world. In the real world, you will see that you will need different kinds of tools, and that there is a whole spectrum. That's good. You will need things like benchmarks that sort of give you an objective assessment of your I/O system's capabilities. But then you will also need applications or tools that let you instrument your application and really, like a debugger and so forth, drill down as deep as necessary to identify the problem. And I'm using two examples here. They are in very different places of the spectrum. H5perf, that's actually part of the HDF source code distribution, is sort of a quick benchmark that you can run on your parallel system just to give you some sanity check. And what I mean by sanity will become clearer in a moment. And then you can take something like Darshan, and that will give you sort of much more detailed information about a running application. H5perf is just a kernel. You don't link that against something. It's just a standalone mini application that gives you some numbers for to feed into your back of the envelope calculations, for example. And of course, with all these profilers and debugging tools, and I'm sure Rob or whoever presented Darshan spoke about that already, there is a compromise. You can have a tool that gives you very detailed historical information. The price that you pay for that is that if you are dealing with a full-blown application, it will distort the performance of that application because there are side effects in terms of time and space in terms of it will change the memory footprint of your application, and then of course the cycles spent in just collecting the data and sometimes compressing them just to keep them around. But then of course to counteract that, if you want less detail, it's less intrusive to the application and in that way more meaningful. But then of course the price that you pay is, you have less detail, it's lower overhead, so it's not going to distort the characteristics of your application as much. But so it's a trade-off, and it's always good to start with something that's rather coarse-grained like Darshan, that gives you sort of a global, time-agnostic view of what's happening, and oftentimes you have already sufficient information to get started right there. In H5perf, this simple standalone application lets you emulate some of these patterns. And there are actually two variants of H5perf. There is a sequential and a parallel version. And for the parallel version, it gives you what I would call the 3 I/O APIs for the price of one, which is that, of course, with HDF5, we are always trying to give you to introduce as little overhead as possible, which in this case would mean that since we are based on MPI I/O, well, it's very unlikely that we will do better than MPI I/O, or when comparing to POSIX, it's very unlikely that we will do better than POSIX. That would be miraculous to some degree. So, but what H5perf lets you do is it will just do a sequence of operations and then just swap the I/O layers. So it will write a data set using POSIX I/O, it will write the same data set, the same pattern using MPI I/O, and then it will write the same data set, same parameters, everything with HDF5, and you can be the judge for, okay, if POSIX I/O in terms of write performance gives you 80 megabytes per second, and HDF5, let's say, gives you 10 megabytes per second performance, that would be terrible. But you can judge for yourself right out of the gate by considering HDF5 for your application, how much you are in the hole just by choosing HDF5. And of course, the reality is that, and again, I encourage you to run this yourself on your system, but the reality is typically that HDF is sort of between 80 to 100%. So depending on the particulars of the read performance, as in many other circumstances, read performance tends to be better than write performance in general. That's not specific to HDF5. But it's typically the HDF performance will be anywhere between 80 and 100% of POSIX performance. Sometimes it's 98, sometimes it's 82. So it depends. Those are the kinds of graphs that you can then produce. This is something that I did when of course, I scavenged some of the slides from the previous presentation at Blue Waters at NCSA. You can make graphs like that. Then, of course, maybe I can be very brief here because you've learned about Darshan already. It's a great way. It's again in this category of tools that is very non-intrusive to the performance of your application and really a great starting point for any kind of performance improvement effort. They're great visualization tools. And I also will be brief here because that's obviously outdated. We are not talking about Blue Waters. But again, an understanding of how much, in the best of all worlds, how much performance can I get out of my system. This is a number that you have to keep somewhere in the back of your mind when you are when your goal is to improve the I/O performance or get more I/O performance out of your application. So this is sort of the OSTs and Lustre. Right, the software, hopefully HDF5 is installed. This is just in the case of Blue Waters. Cray, at least for Blue Waters, is pretty good installing very current versions of HDF5. For HDF5 at the moment, we maintain two major release branches. One is sort of the 1.8x family of releases, and 1.8.17 is the latest release there. And then we just released in March the 1.10 family of releases, and it stands at 1.10.0 patch 1 at the moment. And yeah, I don't know, later in the fall, we'll probably release 1.10.1. Let's see some real applications where we sort of now, with all that knowledge of sort of the methodology and the tools, how do you apply all that in a real application? And again, there are some standard questions to ask yourself again. Sort of what are the I/O layers? We saw that picture. There's HDF5, MPI I/O, Lustre, sort of where do I want to spend my energy? Is there potential for low-hanging fruit? Well, for example, yeah, just playing with the stripe size and stripe count is a low-hanging fruit. So if you can play with that and see if it matters to your application, that's a low-hanging fruit, easy to do. What's your baseline? What are your metrics? So yeah, it's not always, sometimes it is gigabytes per second write performance. That's your only metric. That's the only thing that decides success or failure. That's okay, but yeah, typically these situations are more gray. They are not black and white. Which tools? We talked about H5 perf, Darshan. You can look at other things. Which tools should I consider using to get the information that I will need to sort of plan my next move in terms of performance improvement strategy? And then when do I stop? So when do I have really exhausted to some degree my search space, or the returns that I'm getting have diminished to a point that I'm overrunning my budget, or sort of the next project is coming in the door. Here's an example of one of these particle simulations using the H5 part library. It's well documented in the literature. Here's a reference from 2015, but there are some newer references, a very large sort of plasma simulation. Again, this picture is actually taken from this paper. Sort of what is sort of the structure as far as I/O is concerned of this application? Well, the good news in this case was this is work that was done by Prabhat and Quincy Koziol, who was with the HDF group until recently. He's at NERSC now. And the good news in their case was it was their code. They had total control over all layers. So earlier we talked about that spectrum of control. How much control do you have? Do you use somebody else's library? Do you have some control? You have in-house knowledge that can do something about that, or you have total control. You wrote the code yourself and you can extract an I/O kernel, that kind of thing. So the good news was here, total control. The main challenge here were these large output files. They are sort of multi-terabyte dumps of sort of all the particle velocities and pressures and temperatures and whatnot. And their metric indeed was write speed, throughput. How many gigabytes per second sort of can you push to disk in each sort of time step, or sort of periodically when you wanted to create a time snapshot of the state of the simulation. It is a very computationally intensive application where you have to evaluate all these potentials and whatnot. So in this case, it was unavoidable. Not only did it make sense, it was unavoidable to sort of extract an I/O kernel rather than dealing with the full simulation, because you would have waited way too long to get any meaningful information to sort of adjust your search direction. They were also, as Rob in his presentation mentioned already, faced with this problem that they had these multi-data set writes that they had to deal with. So you probably can't read it, but I see here something like displacements, and the use might be velocities and currents and things like that. They had to write in each time step. And yeah, so kind of the game plan, if you read that paper, that will become clearer, they came up with was to say, well, yeah, let's start with the low-hanging fruit. Let's look at Lustre. and see how many OSTs we can use, if we should vary the stripe size and so forth. And then in the next round, sort of worry maybe about the HDF part of this, or since they were using not HDF directly, but H5 part, this library on top of HDF5, that was sort of the next step. If you look at it logically, of course, they were exploiting, this was a Cray system, and they were exploiting sort of multi-threaded parallelism or thread level parallelism inside of each node, but then had sort of a subset of nodes that would aggregate results to write to disk. And in their case, of course, the optimal, theoretically, situation would be if the number of aggregators that you have matches up with the number of OSTs in your Lustre file system. And that's how this code was written and implemented. And then they found some surprising things. And again, it's some of these things you can do. You should do your model. You can do your back of the envelope calculations and so forth. But sometimes, despite your best effort, things just don't work out. Things just don't work out, and you see something that you initially don't understand. Why is that? So what they found was that it was great to sort of write their checkpoint or their timestamp, and then they called H5F close. They closed the file, and that's where sort of it took a long time. And I apologize, the graph is a little misleading. That graph actually shows you the I/O bandwidth. So if it takes a long time to sort of flush and close a file, that means that your I/O throughput is low. So the red in this diagram was sort of the before thing, before they understood and took some action. It was terrible. It took a long time to close the file. Their target metric, which was sort of write performance as measured in gigabytes per second, was sort of subpar, way below what they would have expected from the system. So the question is, what's going on here? And then, of course, on the upside, I show the picture that once they understood what was going on and we fixed some things for them in the library, the performance went up to a level that was expected and was sort of in line with what you would expect from that Cray system, from that configuration. What happens is the following. In an HDF5 file, we have to sort of, always sort of allocate new storage for new data that's coming in, and we sort of keep track of, at least while a file is open, we keep track of sort of two addresses or two markers. One is sort of the end of allocation, which means up to this point we have allocated HDF data or metadata, and then there is the end of file. And typically you are sort of conservative, or you are saying, well, instead of allocating just what I need, let me just make the file a little bigger because I'm sure it's not going to take long and I will have to write new stuff, and then I don't want to just extend the file quite yet again. So there is the end of allocation and the end of file. Unfortunately, what happens is, at least the way it was implemented before this fix was made, is number one, as part of this H5 close, we called ftruncate in sequential, or the sort of MPI file set size and parallel call. And then we forgot this distinction between EUA and EUF, because it was just simpler to keep one number in the file. And but the fact that we kept just one number in the file in a way necessitated that we did this truncation operation. And that's particularly bad because you could have said, well, that can be easily solved. It can be easily solved by just keeping track of both and not truncate the file in the end when you call H5F close. And that's correct. However, let's not forget that there is a specification for the HDF5 file format out there. And even we, as HDF group, we can change that, but we don't change that sort of nearly every other day. In fact, our major releases are points when we make adjustments, improvements to the file format. But between maintenance releases, so when we go from 1.8.7 to 1.8.8 and so forth, the file format doesn't change, and the API doesn't change either. So it was clear in this case what the problem was, and it was clear what the solution was, but unfortunately, it's not something we could fix directly in that 1.8 family of releases, because as part of our commitment to our users, we will not change the file format sort of behind your back or under the covers, because we have to maintain that compatibility with applications and so forth, and this is something that would have broken applications otherwise. But this is sort of the symptom. And so file truncation, so this is sort of the before and after. So what we do today in 1.10 and so forth, after having learned that lesson, is, well, yeah, we just close the file, we don't truncate it anymore, and we just keep track of both. And so when the file gets reopened, we have already some room to grow into. Typically, there will be a gap between EOA and EOF. Another one is, and Rob talked, and this is not a new idea. Again, PNetCDF had this for a long time, so it's not everything that we use to improve HDF5 is our invention, our idea. We steal good ideas everywhere, every week. Multi-data set I/O, as we saw as part of this VPIC code, they wrote in sort of in batches, relatively large numbers, 6 or 7 or 8 data sets. And what if we couldn't combine these separate write calls into bigger entities? And this is a situation, earlier I said, not to mislead you, that as a heuristic, if you think about collective I/O, when you think about metadata and so forth, this is where it typically has the largest effect, and that's probably true. But in situations like this, if you know that you will write sort of a batch of data sets, not metadata sets, but the metadata associated with that will, of course, also be written, then this can have quite a performance effect. And we introduced 2 new APIs we couldn't do with just introducing a new property list or something like that. We had to introduce, indeed, 2 new API routines, one called H5D read multi and H5 write multi, where instead of providing just a name and an array of one data set, you provide an array of names and an array of buffers for the data sets that you want to write. Here are some sample results, not surprising. It can have a quite dramatic effect. Another application I want to talk about is CGNS. CGNS stands for Computational Fluid Dynamics General Notation System, I believe. And it's one of these community standards, and again, as we saw in the video earlier, one of the sort of the biggest values of HDF5 unfolds when scientific communities, industry standards bodies, they come together and say, we are competitors, and sort of we compete on oil field exploration or something like that, but we don't compete that I use my format and you use your format, and sometimes we work together on projects, but all of us having sort of our own internal standards is sort of creates a lot of friction in this context. So that's why there are industry standards bodies in the aerospace industry, in the oil and gas industry, and so forth out there that define these standards and say, hey, this is how we represent our data, and we compete, but the competition is in other areas, not in file formats. And frankly speaking, as HDF Group, we know how expensive a proposition it is to maintain a file format, let alone HDF in a way is more than a file format. It's really a file format toolkit, because from an application level, you create your own file format. You just use the facilities that HDF offers you to express that. But it's your file format. The things that you put in there mean something to you. They typically don't mean anything to us. So CGNS, Computational Fluid Dynamics, it's an AA in the aviation industry recommended practice. It's an effort to standardize sort of the input and output data in computational fluid dynamics simulation. It covers structured, unstructured, sort of gridding situations, flow simulations, connectivity, boundary conditions, what have you. There are sort of 2 parts to the CGNS standard. There is sort of a standard format that sort of describes how the data is represented and how the data is recorded and so forth. And then part 2 is, the software and sort of the surrounding ecosystem of tools that deals with sort of the visualization, the reading, writing, augmenting, adapting the data, and so forth. CGNS actually started with their own format. It was called HDF. At the time, I think it was developed by General Dynamics at the time. And so they used originally this HDF format. It was sort of, I forgot how when it got started, but at the time parallel I/O wasn't a concern, compression was not a concern, and of course it does not have the kind of support base and tools that we have with HDF today. And at some point the CGNS consortium decided, and they said, well, okay, let's put HDF on some kind of maintenance horizon, but let's phase it out and bring in HDF5. And of course they did some verification and validation studies that HDF could express all the data structures and whatnot, and the performance that they wanted. And in 2013, sometimes in industry things take a little longer sort of to catch on, but they were sort of using clusters and started to do parallel computing with MPI. And it turned out that the performance was actually terrible. And so the question was, well, was it a bad idea to use HDF after all? Well, HDF couldn't have handled it, so there was no real comparison, no real baseline. But the obvious question was, well, why is it? What can we do about it? And if we can do something about it, let's fix it. They funded a project, and one of my colleagues, Scott Breitenfeld, he did this work, and I'll report on the improvements here that we made. So if you CGNS files, again, there's a lot of metadata in the application sense, but also in the HDF5 sense in there. They have, when you represent sort of a CFD simulation, as we said earlier, you have boundary conditions and all kinds of physical constants, and then sometimes experimental setups. This is sort of fluid mechanics. They sometimes use finite elements. They also use finite volumes and sort of geometries. There's geometry, there's topology, there's all kinds of stuff in there. And it's tempting to use the facilities that HDF gives you to neatly arrange things, to sort of group them together and then decorate your variables and your groups with all these attributes. But then depending on the application, you might want to sort of slurp in or prefetch all that metadata to make it available to your tool, which could be a CAD tool, a visualization application. You just want that data present in memory when sort of the analyst or the engineer starts working with it for performance and all kinds of other reasons, but that can take a long time. And so and the same thing happened in parallel simulations, where it triggered what we call sort of this kind of a read storm, where, well, yeah, 10,000 or more ranks would all ask, well, what is this attribute? Read this attribute, and not just read this attribute. They want the whole group structure. They want everything, just that metadata. And as we saw earlier, this HDF5 file, albeit this linear byte stream, the metadata is really sort of scattered all over the place, interspersed. There will be a lot of seeks and small reads and whatnot. And on top of that, attribute reads in parallel HDF5 by default are independent and not collective. So again, independently, tens of thousands of ranks will go out there and go to the same Lustre file system and say, what's that key value pair? So this is what happens on the read side. And there is a similar thing that we call the write storm on the write side. When you close an HDF5 file, so throughout the simulation, they will have created new data, they will have created new metadata, and metadata writes, thank goodness, are collective. However, if you don't do some additional aggregation, there will be individual writes be issued against the file system. And of course, there were some implementation challenges, let me call it that. They were correct, but the implementation strategy, how the underlying HDF implementation implemented there were different strategies. For example, you would keep track of all the metadata, and then you would break them up and have only certain MPI processes write sort of their partition of metadata. Or in the very beginning, there was only process 0 that would be doing the writing and so forth. But the implementation had a lot of challenges there, and it manifested itself as this write storm, this all of a sudden tons of small writes hammering the file system. And here's sort of a little bit of a before and after view of just opening where sort of all these metadata, where in the past that sort of read storm broke loose. This is sort of the red curve, where at some point they scheduled jobs. In some cases, the jobs even didn't get past just opening the CGNS file, so it was that bad. And so, but after we made the improvements in terms of using collective I/O for attribute reads and so forth, this became sort of a more manageable proposition, and it fixed the problem, obviously, for them. So, and here's just sort of a more technical explanations, what I just tried to describe in words. Unlike write operations, read operations are not necessarily required to be collective. So in the CGNS case, for example, if different MPI processes want to read a particular attribute, they do that independently. There is no collective hint to the underlying MPI I/O layer to do that, and that's what shows. So everybody just independently goes out there and says, "Give me this small piece of data," and you have tons of outstanding reads. And so, to avoid that read storm, what we did is we introduced through a property list. Again, we tried not to introduce yet another API. We introduced a property list that you can pass to a read call where it's going to be a metadata call in terms of reading an attribute or something like that. You can pass a property that says, please, or at least try to do this, read this metadata read call collectively. And you can set that on individual objects. You can set this on a whole file basis. You can say, please always try to do metadata, meaning in this case attribute I/O collectively. But you can also, if you have a particular data set that has a lot of metadata, a lot of attributes, you can do this also on some objects, but not necessarily on a sort of wholesale basis for the entire file. And then what happens in this case is that typically rank 0 will issue the write call and then just broadcast everything out there. And again, this is not something new. ParallelNet, CDF, and so forth. Others have done this, but again, we steal the best ideas and try to make HDF better. So here's just something then on the right side, when you do collective metadata writes, and you sort of aggregate many small writes into sort of larger quantities, then you get a good improvement. I'm not getting into talking about the HDF metadata cache. As part of the CGNS standard, they have a standard suite of benchmark problems where they have a particular airfoil or something like that, and they say, for validation, these are the tolerances, and sort of you have to pass that test. But then also in terms of performance, you want to see as you scale this out to sort of tens of thousands in this case of processes, that for the individual elements, like reading the coordinates, or in this case, writing the coordinates, writing the elements, and so forth, there is some scalability there. This is something about HDF5 you have to know. We always try to improve it, and we try to implement new features and so forth, but the somewhat sad truth is that as these things are developed and delivered for a customer, they do not find their way immediately into release. And that's not the customer's fault. To some degree, it's not our fault either. But we are the ones that have to bring these new features or these bug fixes, these improvements into the mainstream release. And so, for example, in the VPIC example, we saw this avoid truncate feature. It's implemented there. They used it back in 2015 in that simulation, but if you were to open the API documentation here and today and look for it, it's not there. Well, why is it not there? Well, it has to do with the release process. So there are when release time comes, typically we have 2 maintenance releases every year. So for example, in the 1.8 family of releases, you can expect a 1.8.16 release that happened, I think I don't remember, early in the spring, maybe in April, and there will be a 1.8.18 release sometime later this year, maybe in November. So we have a 6-month maintenance release cycle. Of course, our engineers, they always work on improving the library, but we implement new features, we work on projects and applications with other companies, and not everything for which there is a Jira ticket in our queue, it's not our goal for all kinds of practical reasons to clean out the Jira queue between maintenance releases. That wouldn't be possible because we are too small a company for one reason, but it would also not be possible because then we wouldn't get anything else done. So every release is in a way a compromise between we fixed this bug and that bug, we have that new feature and so forth. What goes into the release? That's a tough question. And for a small company, also for a big company, I imagine that's not an easy decision. We always have to say, what's the most critical thing for our users that we can deliver at the level of quality that we want to deliver this? Because we can do a shoddy job and sort of cram in a lot of things that are poorly tested and so forth, but we are not doing our users a favor, and certainly we are not doing ourselves a favor that way. And that's why some of the things that I just showed you, it's sad to admit, are not in our main release branches at the moment, but some of them are. For example, this feature to avoid to do collective metadata reads and so forth came out in the 1.10.0 release in March, and the collective metadata rights were included as well. We expect the avoid truncation feature and the multi-data set I/O to come in 1.10.1. For the avoid truncation feature, one thing to say is some of these things can be brought back into the 1.8 release. So if you are a 1.8 user today and you say, I'm going to stick with 1.8 for the foreseeable future, the other sad truth is that certain features cannot be, even though we fixed things by making a file format change, like the keeping track of the end of allocation and the end of file address, we cannot bring this feature back into 1.8. It's just not possible because it requires a file format change, and within a major family of releases at the moment, 1.8 and 1.10, there are no file format changes, never. If you're thinking about jumping on the 1.10 bandwagon, and I think the HPC community or people that use parallel HDF5, I think they are always better off with the latest major release and so forth, then I would encourage you, well, I can tell you that if avoid truncation, sort of closing a file, is a big challenge for you, the metadata being read or written is slow for you, that might be addressed in 1.10.0 already. And then if multi-data set I/O, where you say, my colleague is using parallel netcdf and it's working great there, I wish HDF5 had it. Well, just hang in there just a few more months and you will get it. So that was kind of the main sort of somewhat whirlwind tour of HDF5 and parallel HDF5. To do something real, well, you have to sit down and do vi myprogram.c or work with an existing application. But what I did is I prepared just to give you more of a feeling or show a path how you can experiment with a lot of the features where you might be in doubt and you say, well, I'm not going to change my code to just try this out. No, you shouldn't, and I'm not saying you should do that. But then the question is, well, how can I do that without breaking too much, without writing too much code? I think there might be other answers, but one answer is to use Python in conjunction with HDF5. The H5Py module is very powerful. It works with MPI, and I have prepared a few Jupyter or IPython, as it used to be called, notebooks to walk you through some of the basics, but then also show you a direction in which you can explore the parallel options, including multi-threading, multiprocessing, and MPI-IO. So maybe let me just fire up one of those notebooks. And in the instructions, I said, please go ahead and download your favorite Python distribution. I mentioned the one that I use and that I rely on, which is Anaconda. Installing modules is very straightforward there. And so if you've done that, you can just download the notebooks, put them in a directory, and then in that directory, that will open something that looks like this, where you can browse this collection. And I'll start with the first IPython notebook. I like this environment. Most of you are probably familiar with it. I think it's a very nice and effective way of presenting your work, of exploring things, the documenting things. So some people I've seen prepare scientific publications that way, so I like those notebooks. And they are not limited to Python, by the way. I mean, that's where they have their origin, but I've seen people using them with MATLAB even, or I use them with Lisp, for example. They work just great. Okay, let's look at this. So this is actually, I stole a lot of these examples from Andrew's book, and to get going, you can just execute these cells or these commands listed in here, and if you have hit shift return, it will execute that command and then select the next cell, which helps sort of advancing in this. So the first thing is NumPy is sort of a standard way of dealing with arrays in Python and doing array manipulation type operations. Here in this case, we just want to fake it. We say, let's say we have some kind of a weather station somewhere, and which spews out periodically temperature data, so we create an interesting temperature field here. We can look at this temperature field, and it sort of gives us a snapshot, a printout here, and likewise, let's assume it also generates like wind order of magnitude. It's a scalar here. And now let's stick all that into an HDF5 file. To work with the Python module, with the HDF5 Python module called h5py, of course, we'll import it. And then we create an HDF5 file. The standard way in h5py is to use h5py.file and pass a name of a file. Then you can specify properties like read-only, overwrite, and truncate, and things like that. And then there are other keywords. So in this case, for example, I tell it to use the latest for this Python module version of the HDF5 file format, which is 1.8 in this case. We can talk later about what that means specifically. And then, as Andrew said in his presentation earlier, you can just take the NumPy array and sort of just assign it, sort of speaking in a way, into this file. So F is our file handle, and we just say, well, as a byproduct of this, create a group called 15 in there because it's weather station 15, and create a variable named temperature in there, and take that NumPy array temperature that we have and just write it into the file. And then, of course, this is again a situation where we would like to keep track of all those metadata. For example, we might want to keep track of the units in this case. So this would be this weird ASCII character. It's the degree character. So we say in brackets degree Fahrenheit. We might want to record that we record the temperature every 10 seconds. For example, we stick some kind of sampling rate in here. Then we put a timestamp in here. Again, in Python, we have this nice pool of modules that deal with date time strings and conversions and so forth. So we record the GMT time. Then we do the same thing that we did with temperature. We do that. Oh, I apologize. I hit, I would have noticed at some point I hit shift arrow down instead of shift return. So stuff didn't get executed. And then the same thing, we decorate that with some attributes. And then we can do things like, well, the typical, that's what makes h5py h5py is we get sort of the dictionary syntax on the groups. So if we were to open a file and then we want to discover what is actually in this file, what are the names of the groups, what are the names of the variables in a group, visit individual items. In Python, there is sort of this dictionary style syntax where sort of bracket is the dictionary access, the key to value lookup. So in this case, it tells us that at the file, or and as we would say in HDF, the root group level, there is the station 15, because there could be other weather stations in there. And then we can sort of slice in there, so we can just, I keep doing that. We can slice in there, and so if we go into group 15, it tells us, oh yeah, there's temperature and there's wind, and then we can read the temperature array, and then we can sort of do the standard NumPy slicing and dicing, so I can read the first 10 entries, or I can read them in strides, so 0 to 10, but only every other. And then likewise, as we can do sort of for the members in a group, we can do the same thing, the same dictionary style thing with the attributes. So we can ask, well, what are the names of the attributes? We decorated the temperature data set, for example, with a unit, sampling rate, and a start time. And then we can sort of do the standard Python thing with sort of just iterating over that dictionary and printing name-value pairs and things like that. And then, as good citizens, we will close that file, and that's it. So there are a few others that deal with groups and data sets, and then multiprocessing, multi-threading, and MPI. That's it for now.